May make me a host, madam. Hello. Who's that? Who's on the line? Alan? சொல்லுங்க
Yes, sir.
சரி I know, Alan. Excuse me. Seventeenth group of elements we were learning in the P block. Just give me a moment. We'll have to learn with some of the elements in the halogen family. We have learned with the general introduction in the last class. Now the elements, what we have supposed to learn is chlorine. The first one is chlorine. CHLORIN, chlorine, and it's represented by Cl. Chlorine occurs in a combined state, mainly in the form of sodium chloride in seawater. It is also found in some important minerals like carnallite, horn silver. Carnallite is a double salt, KCl, MgCl2, 6H2O, and horn silver, AgCl. So chlorine occurs in a combined state because it is reactive in the form of sodium chloride, mainly in the seawater. Seawater tastes salty because of the presence of sodium chloride in excess. And it all found in some of the minerals like carnallite and horn silver. Now, the preparation of chlorine in the laboratory, how we can prepare chlorine. What are the methods in which chlorine can be prepared? The first method is by reacting hydrochloric acid or heating hydrochloric acid with manganese dioxide. Hydrochloric acid, when heated with manganese dioxide, manganese and chlorine will react to form manganese chloride, plus chlorine gas will be liberated. So balancing the equation is based on the stoichiometry. 4 moles of hydrochloric acid reacts with 1 mole of manganese dioxide, giving you manganese chloride, chlorine, and water. 1:1:1. See, inorganic reactions has to be memorized or remembered based on their stoichiometry. There is no mechanism to remember this. The second method is laboratory preparation. Laboratory method. Now, laboratory method, the first step is 2 methods are there in the preparation. The first one is chlorine gas is prepared in the laboratory by heating sodium chloride with manganese dioxide with concentrated sulfuric acid. When sodium chloride, manganese dioxide, and concentrated sulfuric acid are heated, what happens is the sodium chloride reacts with sulfuric acid. I can write it as H and HSO4. The sodium will react with HSO4 to form 4 moles of sodium bisulfate. Plus, there are 4 chlorine atoms. Since 4 chlorine atoms, you will get 1 mole of chlorine gas. The other 2 chlorine atom reacts with manganese to form manganese chloride. So this is the laboratory method. So when sodium chloride is heated with concentrated sulfuric acid in the presence of manganese dioxide, chlorine gas is prepared. This is the first method in the lab. The second method is chlorine gas also can be prepared by reacting or heating potassium permanganate with concentrated HCl. When potassium permanganate is allowed to react with concentrated HCl, heating is also not necessary for this reaction. So we get manganese chloride, plus we get 8 moles of water and 5 moles of chlorine gas. So this is the laboratory method of preparing chlorine. The first one is by heating sodium chloride and sulfuric acid concentrated in the presence of manganese dioxide. We get sodium bisulfite, chlorine gas is liberated. The second method is potassium permanganate is treated with concentrated HCl. When we treat potassium permanganate with concentrated HCl, manganese chloride is formed, water is eliminated, and 5 moles of chlorine gas is liberated. This is a laboratory method. The third method we have, that is manufacture of chlorine by Deacon's process. So Deacon's process. Chlorine gas can be manufactured by Deacon's process. Chlorine gas in large scale can be prepared by oxidation of hydrogen chloride, in the presence of atmospheric oxygen. When hydrogen chloride is oxidized in the atmospheric oxygen in the presence of cupric chloride catalyst at 723 Kelvin, chlorine gas is formed. Now 4 hydrogen atom we have, 2 oxygen, therefore 2 water molecule gets eliminated as a byproduct. And since we have 4 chlorine gas, 2 moles of chlorine gas gets liberated. So large amount of chlorine can be prepared by oxidizing hydrogen chloride gas. HCl in gaseous state is called as hydrogen chloride. HCl in liquid will be called as hydrochloric acid. Since it is in gaseous state, it will be called as hydrogen chloride. Hydrogen chloride and oxidation. This is oxidation with atmospheric oxygen in the presence of cupric chloride catalyst. Chlorine is prepared. Chlorine is obtained. Now, coming to the chemical properties of chlorine. We will learn the chemical properties of chlorine. I'll erase all this and then I'll teach you the chemical properties of chlorine. Now, few of the chemical properties, physical properties, I will just tell it out so that you can remember. Chlorine is a greenish yellow gas. In the last class, I told you halogens are colored. So chlorine is a greenish yellow gas, and it has a pungent and a suffocating odor. So it has a very bad smell and it suffocates. When inhaled, it suffocates. And it is heavier than air and it is soluble in water. These are the physical properties of chlorine gas. Now, the chemical properties of chlorine gas we'll have to learn. So we will learn the chemical properties one by one in detail now, chemical properties. The first chemical chlorine with metals and non-metals. The first chemical property is reaction of chlorine with metals and non-metals. Chlorine reacts with number of metals and non-metals to form their corresponding chlorides, to form their corresponding chlorides. So chlorine can react both with metal and also with non-metal. For an example, if we take aluminium, we know that aluminium is a metal. When aluminium is allowed to react with chlorine gas at a particular condition, so aluminium chloride is formed. Likewise, sodium, when we allow it to react with chlorine, sodium chloride is formed. So aluminium and sodium, they are metals. Now, if chlorine is reacted with phosphorus, phosphorus is a non-metal, so we get phosphorus trichloride. If chlorine is allowed to react with sulfur, if chlorine is allowed to react with the sulfur, we get sulfur chloride, S2Cl2. So chlorine will react both with metals and non-metals to form their respective chlorides. The next second set of reaction is reaction towards or affinity towards hydrogen. Affinity towards hydrogen. Now, hydrogen is the gas which is electropositive. Chlorine is the gas which is electronegative. So what happens is when hydrogen is allowed to react with chlorine, hydrogen is allowed to react with chlorine, hydrogen chloride is formed. Similarly, if we allow chlorine to react with the compound of hydrogen, now for an example, hydrogen sulfide. This hydrogen sulfide, when allowed to react with chlorine, we get hydrochloric acid and we get sulfur. Here the charge on sulfur is -2. Here the charge on sulfur is 0. Here the charge on chlorine is 0. Here the charge on chlorine is -1. So chlorine is undergoing a reduction from 0 to 1. -1. When chlorine is undergoing reduction from 0 to 1, it will be called as an oxidizing agent. So we can say that chlorine oxidizes hydrogen sulfide to sulfur. You can see sulfur here, it's -2 oxidation state. Here the sulfur oxidation is 0. From -2 to 0, there's an increase in charge. Whenever there is an increase in charge, it is called as oxidation. So chlorine oxidizes hydrogen sulfide to sulfur. Now what we are going to learn, it is an important question for your 12th standard board exam. Reaction with ammonia. Reaction with ammonia. It's an important reaction. Now, chlorine reacts with we have two here. The first one we will write, chlorine reacts with excess of ammonia. The first condition is excess of ammonia. Excess of ammonia, and liberates nitrogen gas along with the formation of ammonium chloride, So when we take excess of ammonia and it's allowed to react with chlorine, we get 3 moles of chlorine. If we take 8 nitrogen is there and 6 chlorine atoms there. Therefore, we can say we get 6 moles of ammonium chloride. Now, 8 nitrogen, here you can see 6 nitrogen. 2 more nitrogen atoms are there. They combine and get eliminated as nitrogen gas. So this is the first one. Chlorine reacts with excess of ammonia to form ammonium chloride, liberating nitrogen gas. B, excess of chlorine. Here, chlorine is taken in excess. So excess of chlorine reacts with ammonia to form nitrogen trichloride. Now, ammonia is taken in minimum quantity and we take chlorine in excess. When chlorine is taken in excess, we get nitrogen trichloride, that is NCl3, plus we will get 3HCl. So this is an important question. Reaction of chlorine with ammonia. One is excess ammonia and the other one is excess chlorine. With excess ammonia, we will get ammonium chloride, liberating nitrogen gas. This is excess. And with excess chlorine, we get nitrogen trichloride and we will get hydrochloric acid. Now, the next reaction is also an important reaction which is asked many times in the board exams. So we will learn those 2 reactions again. Another 2 reactions, which is important. Excuse me 1 minute. Now, the next reaction is reaction with alkali. Alkali is a base. Base is otherwise called as alkali. Now, these 2 reactions are also important. Now, in this chapter, these are the reactions which can be asked in your board exam. The first one is chlorine reacts with cold and dilute alkali to form a mixture of sodium chloride and sodium hypochlorite. Sodium chloride and sodium hypochlorite. See here, the condition is cold and dilute alkali. With cold and dilute alkali, sodium chloride is formed and sodium hypochlorite. So chlorine, when it's allowed to react with cold and dilute alkali. Alkali is a base. Here, the base what we're taking is sodium hydroxide. Cold and dilute alkali. The product what we get is, we get sodium hypochlorite, CHLORIT, plus we get sodium chloride, and also we get water as the byproduct. NaOCl is called as sodium hypochlorite. Now, the second condition is, if chlorine is treated with hot and concentrated sodium hydroxide. Sodium chloride and sodium chlorate is formed. Chlorate. This is an important question. These two are important. Cold condition, cold and dilute, and the other one is hot and concentrated. So chlorine reacts with hot and concentrated sodium hydroxide. Hot and concentrated sodium hydroxide to form sodium chloride, 5 moles, plus sodium chlorate. Sodium chlorate, 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 plus 3 moles of water. So the difference is only the reagents are same. The conditions are different. One is cold and dilute, the other one is hot and concentrated. So the products also change. Here is sodium hypochlorite and chloride, and here it is sodium chlorate. Now, the next important reaction which you're supposed to remember in chlorine is the reaction of chlorine with slaked lime. Reaction of chlorine with slaked lime. Slaked lime is nothing but calcium hydroxide. Calcium hydroxide is also a base. So reaction of sodium chloride with slaked lime. The next one, reaction of, not sodium chloride, sorry, reaction of chlorine, sorry, with slaked lime. Slaked lime is calcium hydroxide. Chlorine reacts with dry slaked lime. It is not aqueous, it is dry slaked lime and forms bleaching powder. Bleaching powder. So chlorine reacts with dry slaked lime, calcium hydroxide, to form bleaching powder. So calcium hydroxide dry is called as slaked lime. The slaked lime reacts with chlorine to form CaOCl twice. CaOCl twice. This is called as sodium hypochlorite, calcium hypochlorite. Calcium hypochlorite. This calcium hypochlorite and the byproduct is calcium chloride and water. Now the actual composition of bleaching powder. Actual composition of bleaching powder is, you should remember the molecular representation of bleaching powder. It is calcium hypochlorite, calcium chloride, calcium hydroxide, and 2 moles of water of hydration. This is the actual composition of bleaching powder. So how can bleaching powder be prepared? Bleaching powder can be prepared by reacting chlorine gas with slaked lime, dry slaked lime. Dry slaked lime means dry calcium hydroxide. So we'll come, this is with respect to chlorine. Uses of chlorine, it is used in the extraction of gold. It is used in bleaching cotton to make cotton white, bleaching. Bleaching is removal of color otherwise, okay? So manufacturing of dyes, drugs, all these are uses of chlorine. Now the second compound which we have to study with respect to chlorine is hydrochloric acid, HCl. Hydrogen chloride or hydrochloric acid. We have to learn the preparation of hydrochloric acid, and also we have to learn the chemical properties of those. We will learn, and today we should be in a position to finish the P block elements in detail. Possibly in next class we will learn with the MCQs of the P block elements. Now, the next topic is hydrogen chloride, HCl. Hydrogen chloride, HCl. We will divide like this and we'll try to learn maximum possible. Now, hydrogen chloride is prepared by the action of concentrated sulfuric acid on common salt. So when common salt is sodium chloride, when concentrated sulfuric acid is reacted with common salt, sodium chloride, HCl was prepared. This was prepared in 1648. So this is still the laboratory method of preparing HCl. So in the laboratory, in the lab, HCl can be prepared by heating a mixture of sodium chloride and concentrated sulfuric acid. When sodium chloride and concentrated sulfuric acid are heated, sodium chloride is NaCl, sulfuric acid we can write it as HSO4. This is concentrated. So what happens is we get HCl as a product and we get sodium bisulfate as a byproduct. Now this sodium bisulfate which is formed will further react with NaCl. When we say this further reacts with NaCl, what happens is this hydrogen and this chlorine gets eliminated as HCl. And this sodium gets replaced in the place of hydrogen. Therefore, we get Na2SO4, sodium sulfate. This reaction happens at 420 Kelvin, and this reaction takes place at 823 Kelvin. 823 Kelvin. So in the laboratory, hydrogen chloride is prepared by the reaction of concentrated sulfuric acid or by heating concentrated sulfuric acid with sodium chloride. Now, physical properties. Now, what are the physical properties of hydrogen chloride? Hydrogen chloride is a pungent smelling gas. It can be easily liquefied. Therefore, you get hydrochloric acid. And liquid hydrogen chloride boils at 189 Kelvin. This is all not really necessary. And this hydrogen chloride is highly soluble in water. Therefore, it forms hydrochloric acid. Now, the properties, we have to learn chemical properties. Now, in case of chemical properties, we have to prove that HCl is an acid. So the first property, what we're going to learn is called as acidic nature. The first property is acidic nature. Now, HCl, when dissolved in water, HCl donates H plus ion to water to form hydronium ion H3O plus, and we get Cl minus. Proton donors are called as acid according to Bronsted-Lowry theory. Since HCl donates a proton to H2O, HCl is called as an acid. It's a strong acid. Now, one more example if you have to take to prove the acidic nature, when HCl is allowed to react with ammonia, we get ammonium chloride gas. This ammonium chloride is a dense white fume. It's a gas. So ammonium chloride can be condensed to form a salt. So it's a neutralization reaction taking place. Ammonia is a very well-known base, and this is salt, a dense white fumes which is formed. Hence, we can say that HCl, hydrogen chloride, is acidic in nature. Next, this is important. Reaction of HCl with nitric acid. With nitric acid. The nitric acid formula is HNO3. 3 parts of concentrated nitric acid and 1 part of concentrated HCl is known as aqua regia. Is known as aqua regia. 3 parts of concentrated nitric acid and 1 part of concentrated hydrochloric acid is known as aqua regia, used for dissolving noble metals. Dissolving noble metals like gold, platinum, and silver. They can ask you, what is aqua regia? You should tell 3:1. Concentrated nitric acid and concentrated hydrochloric acid is called as aqua regia. The next reaction, what we're supposed to learn is reaction with. Reaction with salts of weak acid. Salts of weak acid. WA stands for weak acid. HCl, hydrochloric acid, decompose salts of weak acid, such as carbonates, bicarbonates, and sulfides. Decomposes carbonates, bicarbonates, and sulfides. Now, for an example, if you take sodium carbonate, Na2CO3, the sodium carbonate, when we allow it to react with HCl. Now, this 2 sodium and 2 chlorine gives 2 sodium chloride. Plus 2 hydrogen, 1 oxygen gets eliminated as water. 3 oxygens there, 1 oxygen will react with these 2 hydrogen to get eliminated as water. The left out is carbon dioxide. So carbon dioxide gas is liberated. Likewise, if you take sodium bicarbonate, NaHCO3, and when this is allowed to react, sodium and chlorine gets eliminated as sodium chloride. This hydrogen, and 1 oxygen gets eliminated as water with the liberation of carbon dioxide gas. Right. Instead of carbon dioxide gas, sulfur dioxide gas will be liberated. That's the only difference between the reactions. Now, uses of hydrochloric acid. Hydrochloric acid are used in the manufacturing of chlorine, in the manufacturing of ammonium chloride, in the manufacturing of glucose. It is used in manufacturing medicines and laboratory reagents. It's used in the preparation of aqua regia. These are the compound. This is with respect to hydrogen chloride. Now, in the 17th group, we have the last part of the topic that is called as interhalogen compounds. What is this interhalogen compounds? These interhalogen compounds are formed by a combination of halogens amongst themselves. They are formed by combination of halogens among themselves. So interhalogen compounds. So when halogens react with each other, the compound formed is called as interhalogen compounds. Generally, we represent interhalogen compound as XX dash, XX dash thrice, XX dash 5 times, and XX dash 7 times, X dash 7 times. Now, X is a halogen. X is a halogen with larger atomic size. What is this X? X is a halogen with larger atomic size. And X dash is a halogen with smaller atomic size. Now, and smaller the atomic size, electronegativity will be high. If fluorine is X dash, fluorine is small and electronegativity of fluorine is high. X is a halogen with larger atomic size. So interhalogen compounds are formed by the combination of halogens amongst themselves. So we will learn about the preparation of interhalogen compounds now. I'll erase this and then we will learn about the preparation of interhalogen compounds. So the preparation of interhalogen compounds we will learn now. Preparation of interhalogen compounds. Interhalogen compounds are prepared by the direct combination of halogens amongst themselves or by the action of halogen on lower interhalogen compounds. One is by direct combination of halogens amongst themselves, or by the second method is by the action of halogens, on lower interhalogen compounds. Lower interhalogen compounds. So how can we prepare interhalogen compounds? Interhalogen compounds can be prepared by direct combination of halogens or by the combination of halogens with lower interhalogen. There are so many examples to be learned. So one of the examples is chlorine is a gas and fluorine is also a gas. Equal volumes. So we get 2 moles of ClF. X is Cl, X dash is F. X is larger, X dash is smaller. And this is called as, this is also in Keshe state, this is called as chlorine monofluoride. It's called as chlorine monofluoride. Similarly, the second case, if you observe, chlorine, when treated with excess fluorine, and this is happening at 573 Kelvin. So we get 2 moles of ClF3. This is called as chlorine trifluoride. Now, the second method, if you observe, action of halogens on lower interhalogen compounds. When we say action of halogen with lower interhalogen compounds, this third example we will take, that is ClF, which is a gas. It's a lower interhalogen compound. When this is treated with fluorine at 475 to 575 Kelvin, we get ClF3. This is again chlorine trifluoride. This is the third example given in the text, which is required. The fourth example is bromine is a liquid. This bromine, when allowed to react with excess fluorine gas, or not excess fluorine gas, diluted with nitrogen. So we get 2 moles of BrF3. This is called as bromine trifluoride. It's called as bromine trifluoride. The fifth reaction method, there's a lot of methods to be prepared. The fifth method, they can ask you what is an interhalogen compound, give 1 or 2 examples of interhalogen compound. So I'll give you the last example. If I keep on writing, it goes on. So bromine is a liquid when it's allowed to react with fluorine. Here, fluorine is excess. So we get 2 moles of BrF5. It will be called as bromine pentafluoride. Now, the structures you should remember. The structure of any interhalogen compounds depends on the hybridization. Now, if you take XX dash, and if it's a linear molecule. If you take XX dash 3 times, the hybridization is sp3d. When we say sp3d, it has a T shape. And if you take XX dash 5 times, the hybridization is sp3d2. it is square pyramidal. Square pyramidal. And if you take x dash 7 times, the hybridization is sp3 d3, it is pentagonal bipyramidal. So structure of the complex depends on the hybridization. Hybridization. Now this is with respect to group 16. So 16th group of the compound in P block, we have learned, we'll have to learn the 18th group. We will finish off 18th group today, so that we will solve the MCQs in the next class and continue with the next topic later. Now the next group is 18th group element. This 18th group elements are also called as noble gases. This 18th group elements are also called as zero group elements. This 18th group elements are also called as rare gases. So the next what we have is the 18th group elements. This 18th group elements are called as noble gases, inert gas. It's also called as a rare gas. It's also called as zero group elements. Noble gases, because in the earlier days, we understood that their reactivity is very, very low. Therefore, they do not react, they said. Therefore, it is called as noble gas. Since it is not reacting, otherwise it's called as inert gas. And rare gas, very trace quantity present in the atmospheric air, therefore it is rare gas. And also we have zero group element. Now, helium, neon, argon, krypton, xenon, and radon are the elements present in the 18th group called as noble gases. And in case of radon, radon is a radioactive noble gas. Now, what is the source of noble gas? The source of noble gas is air. From where noble gases are obtained? From the atmospheric air. So in case of the noble gases, we have helium, argon, neon, argon, krypton, xenon, and we have radon, which is radioactive. So from noble gases, we are expected to get only 1 mark question in your board exam, and that will be from part A, question number 8. So we will not discuss about these noble gases in detail. We will learn about some of the reactions of noble gases and the preparation of noble gases. Now, firstly, you should remember the ionization enthalpy of oxygen and xenon are same. Now, what was happening was when oxygen is allowed to react with, in fact, oxygen is allowed to react with platinum hexafluoride. Oxygen, platinum hexafluoride complex, we got this complex. So now, since the ionization enthalpy of oxygen and xenon are same, that means even though we understood that it has got inert gases or noble gases or non-reactive gases, now the ionization potential of oxygen and xenon is same. If oxygen can react with platinum hexafluoride, it means xenon also has to react. So that was the idea in which Neil Barrett is a scientist who prepared the first noble gas compound, NEILBARTALETT. Neil Barrett is the first scientist who prepared the first noble gas compound. Since oxygen and xenon have same ionization potential, what he did was he allowed to react to xenon with platinum hexafluoride. Now, when xenon is allowed directly to react with platinum hexafluoride, a noble gas compound was prepared, the first noble gas compound, that is XeP plus PTF6 minus. So this is called as xenon. They can ask you IUPAC name of this complex. Xenon hexafluoride fluoridoplatinate. Oxidation number is 5. Hexafluorido, xenon hexafluoridoplatinate, 5. So they can ask you the preparation of noble gas compound, or who prepared noble gas compound. You have to remember the name of the scientist who prepared the noble gas compound is Neil Barrett. Now, compounds, see, there are a lot of reactions to be learned in noble gas compounds. So you cannot lose 1 mark that way in part A. So kindly follow. The first one is compounds of xenon. Compounds of xenon. Now, xenon, which is a gas, reacts with fluorine in the presence in a nickel tube, NiCk, nickel tube at 673 Kelvin and 1 bar pressure to form xenon difluoride. It is a solid. Similarly, see the ratio is 2:1. The ratio is 2:1. Here, xenon, if it's allowed to react with fluorine gas in the ratio 1:5. Don't go based on the stoichiometry. You should not say 1:2. Stoichiometric ratio is 1:2. It is not based on the stoichiometric ratio. So this also in the presence of nickel, in the nickel tube at 873 Kelvin and 7 bar pressure, we get xenon tetrafluoride, which is a solid. Now, similar reaction, xenon, when it's allowed to react with fluorine, it's all in gaseous. This is a gas. The ratio 1:20 in the nickel tube at 575 Kelvin and 60 to 70 bar pressure, we get xenon hexafluoride. This xenon hexafluoride is a solid. Now, the xenon hexafluoride also can be prepared by one more method. They can ask you to fill in the blanks type question they can ask you here. So pay attention and learn all these reactions. Xenon hexafluoride can also be prepared by the reaction of xenon tetrafluoride with oxygen, dioxygen difluoride. Dioxygen difluoride, O2F2. So what happens here is, now we will get XCF6 with the liberation of oxygen gas. Here this XCF6 is solid. So xenon tetrafluoride, when reacted with dioxygen difluoride, you get xenon hexafluoride. So this is the reaction of xenon compounds of xenon. Only we have learned with xenon reacting with fluorine and xenon reacting with dioxygen difluoride. We have to learn now some complex reactions and shapes of some of the noble gas compounds. So we'll finish that today quickly. Did you follow this? And Lakshmi, did you follow? All right. Now, the next is the reaction properties of xenon fluoride. Properties. Now, what are the properties of xenon fluoride? All xenon fluorides are colorless. It's a crystalline solid. Whether it's xenon difluoride, tetrafluoride, or hexafluoride, they're all solids and they are colorless. They are powerful fluorinating agents. They are powerful fluorinating agents. When we say they are powerful fluorinating agents, which can give fluorine, will be called as fluorinating agents. So xenon tetrafluoride, when it's allowed to react with sulfur tetrafluoride, we get xenon and we get sulfur hexafluoride. So this will give fluorine to sulfur tetrafluoride. So therefore, xenon tetrafluorides or xenon fluorides are a very good fluorinating agent. Now, for an example, if you take xenon tetrafluoride, if we allow it to react with platinum, we get xenon plus we get platinum tetrafluoride. So since they can give fluorine easily, they are called as fluorinating agents. Now, second point is they are readily they are readily hydrolyzed. They are readily hydrolyzed even by trace amount of water. They are easily hydrolyzed even by trace amount of water. If you take xenon difluoride, which is a solid, even in the presence of traces of water, we get xenon, which is a gas, and we get HF, 4 moles of HF aqueous, and we get oxygen gas. Oxygen, yes. We should remember these kind of equations for balancing. They can ask you for 1 mark. Similarly, if you take xenon tetrafluoride, and if this is allowed to react with water, it gets hydrolyzed to form xenon trioxide plus 6 moles of HF plus F2. Now, in this type of questions, you should be in a position to only balance the equation. If you are in a position to balance the equation, then you will get the correct answer. In case of what balancing, if at all they ask. The next is xenon fluorides. Reacts with fluoride ion. Acceptors. Fluoride ion acceptors to form cationic species. Cationic species. Now, for an example, we take HCF2, and if it's allowed to react with phosphorus pentafluoride, we get a complex like this, HCF plus we get PF6 minus. So compounds are formed. Cationic species. They are cationic species. Now, last part of the topic we have, that is the xenon oxygen compounds. Let me check if I have. Xenon oxygen compounds here. Compounds of xenon and fluorine we learned. Now we have xenon oxygen compound. We learned all this. Xenon oxygen compound. Now, there are 2 reactions. Xenon tetrafluoride and xenon hexafluoride, they undergo readily hydrolysis. They undergo hydrolysis readily. When we say they undergo hydrolysis readily, xenon tetrafluoride on hydrolysis with 12 moles of water. This is important, very important. This request. We get xenon trioxide, 24 moles of HF, and 3 moles of water, or 3 moles of oxygen. Similarly, xenon hexafluoride on hydrolysis gives xenon trioxide, 6 moles of HF. So this balancing the equations, you should remember. The last one, what we have is xenon oxyfluoride. Now, when we say xenon oxyfluoride, xenon hexafluoride on hydrolysis gives xenon oxyfluoride plus 2HF. From 6 fluorine, 2 fluorine reacts with hydrogen to form 2HF. Therefore, we get xenon oxyfluoride. Likewise, if we take xenon hexafluoride, if it's hydrolyzed with water, complete hydrolysis, this is partial and this is complete hydrolysis, we get xenon HCO2F2 plus 4 moles of HF. So these 2 reactions are very important. And structure of xenon compounds, you can just go through the notes so that you can answer any question based on the structure of noble gas compounds also. So here we end the chapter P blocks elements. We will learn with the MCQs possibly tomorrow maximum, and then we will learn. So shapes or geometry of the xenon compounds you have to go through from the textbook. That is based on hybridization. XeF2 is linear. I will just write this is linear. The hybridization is sp3d. It is sp3d. It is not any other. This is different because we have lone pair of electrons. XeF4, here it is sp3d2, and it is square planar. It is not as the geometry what we have learned it in coordination chemistry. XeF6, the hybridization is sp3d3, and it has distorted octahedral. Please remember these structures, and you can go through the books. XeO3, this is sp3 hybridization, and it's pyramidal. It's pyramidal, it's not tetrahedral. Expected is tetrahedral, but it is not tetrahedral. So XeOF4, hybridization is sp3d2, and here they have square pyramidal. Square pyramidal. So this ends the topic, and also uses of some of the noble gases you can go through. What are the uses of noble gases in the material textbooks? It will be there so that you can answer any of the questions they asked. From noble gases, as per the discussion from the board, it should be for 1 mark. Anyways, we will stop with the class here. Ma'am, I'll stop the class, ma'am. Thank you.